Okay. Good day, everyone. This video is for the purpose of practicing for my upcoming reporting for my graduate school class, Math 202.1, in Advanced Calculus. So, my name is Brian. I'm the student. Then let's get started. So, yeah. We do have a problem that we need to solve, and there are key tools for solving the problem. So the first one is using the consequence of the completeness axiom. What does that include? So every non-empty subset of R, the real numbers that is bounded below, has the a greatest lower bound, and the GLB can be called as the infimum in R. Okay, so why is it important? So the consequence of the completeness axiom guarantees the existence of the infimum of a set for any non-empty set S in R that is bounded below. So the existence is very important for that. And then you might be asking, Brian, what do you mean by lower bound? So a lower bound, we have to define S as a non-empty subset of the real numbers again, and we say that S, that set, is bounded below if there exists a number M such that that number M is less than for all the elements S in big S. In that case, M is called the lower bound of the set S. And then in pictures, we can see here that M is less than for all elements S1, S2, S3, and so on. Okay, so that's the elements of S, and you can see the banded green here is the set S. So what do you mean if we call a lower bound the infimum? So what is the infimum of S? So we have to define the set first. Set S is the non-empty subset of the real numbers, and that set is bounded below. The number U is the infimum or the greatest lower bound of the set S if, number one, U is a lower bound of S, and number two, for any other lower bound V of S, we have U is greater than or equal to V, meaning U is the greatest among all of the lower bounds. Symbolically, in logic, if you want to remember this definition, you can write it as U is equal to the infimum of S if and only if, first, U is less than or equal to S for all S in S. That's the lower bound condition. And for all V lower bound, V is less than or equal to U. In pictures, one can notice that all green points are lower bounds of the set S, but none are greater than or equal to U, meaning they are all in the left side of the number U. Okay? And then it's very hard for us to prove that a set is the infimum or a number is the infimum. So there are equivalent characterizations for that definition. So that if it's hard to prove it directly, the one point, then you can choose other definitions to make the definition proven. So let's get started. So we call this lemma 1 in our proof. Alternative definitions of the infimum of S. So for a lower bound U of a non-empty set S of the real numbers, the following are equivalent. This is actually a theorem that you can prove, but that's um, outside of the scope of this discussion. So number one, U is equal to the infimum of S, and you can say it like this: for all V, or for all number V greater than the infimum U, so it is not, is no longer a lower bound. So there should be an element S between U and V such that it's in the middle. So how we say that is V is greater than S. So in pictures, you can see here, the only reason why I put a picture here is because this is the one that I'm going to use in the proof of the problem. So there's a number s, which is s1 in this picture. It's greater than or it's less than v, the number v that we chose, and it's greater than u, essentially. So it's in the middle. And then the last one is that we are using epsilon. For all epsilon greater than 0, there exists an s in S such that S is less than U plus epsilon. This definition is very important if we want to use the epsilon property or even the Archimedean property, which is outside of the scope of this problem. But that's usual. That's useful for that scope. Okay. So we have the assigned problem for the day. So the problem is let A be bounded, non-empty subset of R, and S be a real number. Show that the infimum of S plus A is equal to S plus the infimum of A. So it's hard for us to illustrate to think of it by, of course, by seeing the problem. So in analysis, it's good to draw it as pictures, and I took the liberty to illustrate it in this example. So the blue segment is set A. The red one is S plus A. So the blue segment represents A, and the endpoints are the infimum and the supremum respectively, and the red segment represents S plus A, which is a translation of A by S on the positive side. So clearly, one can say that the infimum of S plus A is equal to S, the number S, plus the infimum of A. It might be hard to distinguish that on this picture, but I've provided a numeric example. So the blue segment is the interval 1 comma 5, and the red segment is 4 comma 8, which is S plus A. It's a translation of A by S equals 3. So if you notice, you just added 3 to 1 and 5 to get the other interval. So clearly the infimum of A is 1, supremum is 5, and then the infimum of S plus A, based on the picture, is 4. But you can see that the infimum of S plus A is equal to S plus infimum of A, such that S is equal to 3, infimum of A is 1, so it's 4, which is what you can see in the illustration. Okay? So we proceed in proving the problem. So let A be a non-empty subset of the real numbers and S be a real number. That's just a shorthand notation. And assume A be bounded. That's a part of the problem. And therefore, it is also bounded below since it's bounded. So from earlier observations, since A is not empty and bounded below, by the consequence of the completeness axiom of R, this guarantees the existence of the infimum of A, and let's call it W. We want to show that the infimum of S plus A is equal to S plus infimum of A, and we call it star. So if we're handling infimums, it's better to define what is our set. Since S plus A is a cumbersome notation wise, we call it T. T is equal to the set of S plus A, wherein A is in A. Small a is in A. In order for us to show star, we must show that S plus W, which is the infimum, is the greatest lower bound of the set T. So how do we proceed in doing that? So we need to show that. So for any element T of big T, there exists an element A in big A such that T is equal to S plus A. Since W is the infimum of A, so W is less than or equal to A for all A in A because it's a lower bound. So what we did here is we add S to both sides, and we notice that A plus S or S plus A is equal to T, which is S plus W is less than or equal to T for all T and big T. So that tells us that S plus W is a lower bound of the set T. And in the other hand, we want to show that it's the greatest lower bound. So if we want to show that something is the greatest, then by contradiction, let's assume there's another number greater than what we're assuming as the greatest. So by way of contradiction, say v is another lower bound of t such that it's bigger than s plus w. And since that's the number, we can subtract s to both sides. And we notice that by lemma 1 number 2, since w is the infimum of a and v minus s is greater than w, so there exists an element a in big A such that v minus s is greater than a, then we add s to both sides and we notice that s plus a is in t. So you can see that the greatest lower bound or another lower bound is greater than an element of the set. So this is a contradiction to the definition of the lower bound because every element of the set should be bigger than the lower bound. Hence, s plus w is the greatest lower bound of t. In other words, infimum of t is equal to s plus w. But that's not what we want to prove. We want to prove its original statement. So we have to substitute what is t and w. So therefore, we got what we're being asked. Okay, and that's pretty much it on this video. This is just a practice of the reporting, and these are my references for what I've read in order for me to understand how to solve the problem, and that's pretty much it. If you have any questions, please leave down a comment below and have a great day. Bye bye now.